All right, thanks everybody for being here. And we are starting another session of the Machine Learning Coffee Seminar for FI. And we are extremely excited to have here with us today Laurence Aitchison, who is a senior lecturer in computer science at the University of Bristol, and is part of the Bristol Computational Neuroscience Unit. And Laurence is going to talk to us about his recent work on deep kernel machines. And yes, up to you, Laurence, and thanks again for coming.
Yeah, fantastic, thanks. I should say this is joint work with Sebastian Aubert, who's from Cambridge. Technically, he's supposed to be in Carl Rasmussen's group, but then Carl disappeared off to Second Mind, and Maxine Robbins and Adam Yang, who are PhD students with me. Okay, so to motivate deep kernel machines, we need to sort of take the 10,000-foot view of machine learning. And if we think all the way back to sort of pre-2012, there were broadly kind of two different classes of methods that we used. So we used shallow feature-based methods, potentially with some sort of fixed hand-chosen nonlinear feature extractors, and then did something like linear regression on top of them. Or alternatively, we had kernel methods, shallow kernel methods. So these are things like Gaussian process regression or kernel ridge regression. So in both linear regression and these shallow kernel methods, you need to choose a good either feature extractor in the linear regression land, or for a kernel method, you need to choose a good kernel. So if we think about a support vector machine, then if I choose a linear kernel, I'm going to get a linear decision boundary. If I choose a polynomial kernel, I'll get a sort of a different class of decision boundary. And again, for a radial basis function kernel, I'm going to get again a different family of decision boundary. And my choice of kernel is then going to have a big effect on the decision boundary, and then a big effect on the performance of the ultimate method. And the exact same thing happens if I think about, say, Gaussian process regression. If I have a squared exponential kernel, then I'm going to get these nice smooth functions. If I have a Laplace kernel, I'm going to get these very rough functions under the prior, and that's going to have big implications for the performance of the final method. Now, the problem is that in this brave new world, we care about very, very complex inputs, things like images or sounds. And sort of up until, again, about 2012, people tried very hard to come up with good either feature extractors or kernels for these types of data. And it turned out that basically they couldn't, or at least the performance of anything they came up with was far, far, far worse than even basic things like deep neural networks that appeared in, say, 2012. So the conclusion is really that these shallow methods with fixed feature extractors or kernels really aren't sufficient, and that we need flexible, learned feature extractors or kernels if we're going to reason about these types of very complex inputs. So let's go back to this table now. So to get these complex learned feature extractors, we know how to do that. We go to the deep, or we make the network, we make the model deep, so we stack many layers of linear regression with nonlinearities, and that gives us a deep neural network. But I mean, to my mind, this raises the question of, well, what lives in this fourth spot down here? What lives in the bottom right? What does it mean to have a deep generalization of kernel methods? And that's really what I'm going to try to describe to you and explain how to do in this talk. And so to get there, I'm going to start by reminding you of how we might get, say, a kernel method like Gaussian process regression from a feature-based method like linear regression by sort of the process of kernelization, by integrating out the weights. Then I'm going to do something similar in this deep neural network setting, and it's going to turn out that in a very similar way that Gaussian process regression can be understood as linear regression where I integrate out the weights, then there's going to be a very similar understanding of how deep kernel machines are equivalent to deep neural networks in a particular infinite limit. Then I'm going to talk about the potential advantages of deep kernel machines, and these really come under three headings. So that's interpretability. Deep kernel machines are likely to be much more interpretable because they work with kernels, and at least to my mind, kernels are much more interpretable than features or weights. Unimodality, we have strong reason to believe that the deep kernel machine loss is actually unimodal, which is very nice. And then fast optimizers. Because we now have a unimodal loss, we get to be very clever about the optimization we do, and we can apply some tricks to massively speed that up over basic gradient descent-based methods. Okay, then, let's get started with this point one. Just a little reminder of linear regression to Gaussian process regression. Okay, so in the Bayesian linear regression setting, we have a very simple model like this. There's no intermediate units, so there's just inputs here, and this is a batch of input vectors, so we have multiple features for each input, and we also have multiple sort of input examples here batched up into that matrix. And then we have then a batch of outputs, which is now a vector y, so there's one output for each training example, and then I get this y by multiplying those inputs by a weight vector. And I'm going to sample, or at least under the prior, I'm going to assume that this weight vector is IID Gaussian, and I'm going to divide the variance here by the number of input vectors, just so that the outputs behave sensibly for any number of input features. So the outputs have roughly the same scale, no matter how many input features we have. So the key sort of Gaussian process trick is to say, okay, I can actually rewrite this prior by integrating out the weights. And if I do that, I end up with a distribution over the outputs now. And this distribution is very intuitive. So it says something like, if my inputs are similar, then I'm going to have a high covariance, I'm going to have a high correlation between those outputs. So if my inputs are similar, it's likely that my outputs are going to be similar as well. And there's another consequence here, which is something that we're going to use again and again and again. And that's that this expression at the top here, this Gaussian process view, actually describes everything we need to know about the system. And if you notice here, all we need is this training example by training example matrix here, which is this XX transposed. And we can call that a kernel matrix there. And that means we don't need that full input vector. And again, that's something we're going to use many times, because in deep neural networks, we're going to find that, again, we don't need like the intermediate layer features. We only need the corresponding sort of kernel or ground matrix, which is going to be features times features transposed. Okay, so that's the sort of zero hidden layer case. What about having one hidden layer? So what happens in this case now, where I'm taking the width of this hidden layer to infinity? Well, again, I've got a batch of input vectors x. I'm going to consider a sort of general infinite hidden layer. So I'm going to take those input vectors, I'm going to multiply it by a weight matrix, and I'm going to apply a pointwise nonlinearity, perhaps a ReLU. And then my output is going to be given by exactly the same process that we saw before on the previous slide. So we're going to take those h's from that previous layer, and we're going to multiply by a weight vector to get a single scalar output for each training example. So now if I ignore what goes on in this bottom bit down there, and I treat those h's in the middle as the input, then actually I end up with exactly the same model that I saw on the previous slide. Oh, sorry, the weights are IID Gaussian. Yeah, so if I ignore what goes on the bottom, then I can treat these h's as the input, and I can just apply the same results from the previous slide. And that means that my y's here are given by a Gaussian, where that kernel in there is again HH transposed. So that again tells us that my y's are going to be correlated if that intermediate layer features are similar. But of course, things are actually a bit complicated because now I don't know what this K is. That K comes from those H's, and those H's down here depend on those weights. So what can I do? Well, it turns out that in the infinite width limit under the prior, I can actually deterministically compute K. And this was originally done by Radford Neal way back in sort of 1995. So the idea then is I'm going to compute K in this limit as that intermediate layer goes to infinity. So if you remember, this is the definition of K. And then, this is kind of the key trick, I can write this out as a sum. I can write this matrix product as the sum over each feature of this outer product. So this is just rewriting that matrix product. So now, this first part is the average of infinitely many terms, because I'm dividing by n1 and summing over n1 up there. And each of these h lambda transposed is IID. If I look at this h lambda transpose, so an individual h lambda is the activation of one feature, let's say this one, for each training example. So if you look at each of these vectors now, each of them just depends on those input weights, and those input weights are IID. And so that means that each of these h lambdas is IID. I am, of course, conditioning on the input when I say this. And so that means I now have an average of infinitely many IID terms, and by the law of large numbers, that's just equal to the expectation over any one term. So in some ways, this doesn't seem to have helped us because I still have to compute this potentially quite complicated expectation. So I'm going to slightly skip over this bit in the interests of time, but it turns out we can actually compute these expectations for a very large class of nonlinearities or even kernels as well. So Cho and Saul tells us how to do this for things like the ReLU kernel that we care about for neural networks. And even better, they find that the kernel that results depends only on this XX transposed again. It doesn't depend on the underlying features, which is a very useful property that we're going to exploit later. I should say that it's difficult to see why that should be the case, sort of just based on this diagram. And it's going to turn out that this same property that you can compute the kernel from this product of the features also holds for any isotropic kernel or any distance-dependent kernel if we're thinking about a sort of more Gaussian process setting as opposed to a more deep neural network setting. But yeah, if you want more details on this point, please do look at the papers. Unfortunately, I'm gonna have to skip over it for now. Okay. So then, once we have that basis, we can think about what happens in a deep neural network. So I'm now going to separate things out slightly. So we have a batch of input vectors x that are going to have these f's, which are the previous layer multiplied by some weights, and then h's, which applies the nonlinearity. And then again, f's, which are the previous layer h's multiplied by some weights, and then my h's, which are the f's, with the nonlinearity applied. Then again, I'm going to have a single scalar output, which is my top layer, h's multiplied by some weights. So then the question becomes, what happens in the kernel domain? Can I sort of write everything in the kernel domain? And the answer turns out to be yes, at least in this infinite limit. Okay. So we start off by writing the kernel corresponding to the inputs, as before. And then in the infinite limit, it's going to turn out that the outer product of these f's, which I'm going to call here g, is equal to the kernel at the previous layer. And then the outer product of these h's after this nonlinearity, I'm going to call that k, is some function now applied to the G, the ground matrix, from the previous layer. And so this was a function, for instance, from Cho and Saul. Then we can do exactly the same thing at the next layer. So the outer product of those F's, which I'm calling G, is equivalent to that kernel from the previous layer. And then the outer product of the H's, which I'm calling K, is that nonlinear transformation of the previous ground matrix, which might come from Cho and Saul. And then we finally take that K2, that final top layer kernel, and that becomes the Gaussian process kernel that we use at the end. Okay, so we can then, so this means that we can actually write everything down in the kernel domain. And so for simplicity, I'm now going to strip away all of the feature stuff and just think about what happens in the kernel domain. So now the problem here is that this process is entirely inflexible. So this K0 is just equal to that XX transpose. There's no flexibility there. There's no learned parameters. There's no stochasticity from a prior. Likewise, I'm setting G1 equal to K0, no flexibility. Then K1 equal to this nonlinear transformation. I mean, this nonlinear transformation is just a function. Cho and Saul wrote it down. Again, there's no parameters in there. There's no stochasticity. There's no flexibility. And so then all the way through, we end up with a deterministic top layer kernel. And that happens in the prior, which is kind of bad, but maybe okay. And it also turns out happens in the posterior if we condition on Y. And this is now really bad because it means there's no representation learning. That top layer kernel is just a fixed function of our inputs. And it also, incidentally, explains the poor performance of infinite neural networks. So these things have been studied in quite a large body of work now. And it turns out they all perform quite poorly relative to corresponding deep neural networks. And technically what's going on is that as we take this, is that we're taking this infinite limit for width, and that in effect is overwhelming any influence of the prior. So as we infinite limit, those sort of kernels in here, or this kernel here, is going to approach, the ground matrix approaches the kernel by that law of large numbers, and then there's nothing that a very small finite amount of data can do to change that. Okay, so then perhaps the key trick with deep kernel machines is how to overcome this fixed top layer kernel. And the way we do that is by copying the data infinitely many times as we take this infinite limit over layer width. So I'm now, in a sort of technical Bayesian sense, conditioning on infinitely many copies of the data. So it's not really Bayes anymore, but sort of whatever, we can think about how to take this further. And if you want to ask me about the sort of true Bayesian version of these things, you can ask me at the end, because we have got that variant as well. It's just more complicated. Okay. And so now in this setting, the prior doesn't overwhelm the likelihood because we're copying it infinitely many times and being careful about how we take this limit relative to the limits of the intermediate layers. And then this posterior over K2 does depend on those y's. And in particular, what happens, this function in here remains deterministic, but the ground matrix, which if you remember, oh, sorry, those two there are the wrong way around. Anyway, the ground matrix depends on the features, and the features depends on the weights. So that ground matrix is then going to be close to, but not exactly the same as the kernel at the previous layer. And likewise, this ground matrix here is going to be close to, but not exactly equivalent to the kernel at the previous layer. And that means we have representation learning, but at the same time, the posterior, it turns out, remains a point. So we still know that the posterior then over K2 is just some particular value of K2. And that's because we've taken this infinite limit, which causes things to behave relatively strangely. but it is nonetheless very useful for getting sort of nice analytic computations. Okay. So practically then, how does this work? Well, it turns out that exact inference in this slightly weird network where I've copied the data optimizes an objective. And you can get this actually either from variational inference or from Langevin sampling. And it's from Langevin sampling that we can say that this is actually exact inference as opposed to some approximation. And that objective looks something like this. So let's split this down into terms now. So first, we're optimizing over these Gram matrices. So in effect, we're computing the posterior over Gram matrices, and we know that this posterior is a point, and we can find that posterior by optimizing this loss function over these Gram matrices, which describe those intermediate layer representations. And we've got a likelihood here. So that encourages good performance on the data, so it encourages us to find a top layer representation that somehow works well for the data. So that gives us our representation learning, and it makes us happy. But I'm actually optimizing over generic Gram matrices here. Gram matrices can do anything as long as they remain positive definite. And that means I need very, very strong regularization in order to stop crazy things happening. And that comes from this tail divergence term here. So if you remember, under the prior, we actually had the next Gram matrix was equal to some nonlinear transformation of the previous Gram matrix. Now we're relaxing that a little bit, and this tail divergence is going to penalize differences between this and this, but it is going to allow there to be some differences. It is going to allow there to be some flexibility, as long as that flexibility is helping us improve performance. And then finally, we have these new L terms. So they control the strength of the regularization, and they correspond to the layer widths. So we can still have different factors. So as we take the width to infinity, we can still have some layers, say, being twice as large as other layers. And these new L control those differences in layer widths. And before we get going on to sort of more practical considerations, it's worth noting that this has a lot of potential for the theory of neural networks. So I'm not sure if anyone is aware of this literature, but I mean, physicists do a lot of thinking about finite width neural networks, and they apply lots of very, very complicated perturbative approaches. And ultimately, it's all really hard. And it's really hard because they're trying to consider the finite width setting. So here we've got what is really an incredibly simple objective compared to the pages of algebra that they've come out with. And we've done that by taking a clever infinite width limit that nonetheless mirrors what should be going on in the finite width setting. So I'm also really excited about this, but it's not going to be the focus of the rest of the talk. Okay. So then, unfortunately, there's the obligatory performance slide. So what I'm doing here is to develop a scalable inducing point variant of the deep kernel machine. And it turns out you can do this relatively straightforwardly because there's a variational inference interpretation of the objective. So we can sort of plug in to variational inference-based inducing point Gaussian process methods relatively straightforwardly. So I'm using 300 fixed inducing points and a two-layer architecture with skip connections and a squared exponential kernel. And I'm evaluating using root mean squared errors. So we're not really Bayesian here because I'm copying that data infinitely many times. And so it isn't clear whether we get the same protection against overfitting that you would in proper Bayesian methods. So I'm not, for instance, comparing against sort of full Bayesian deep Gaussian processes. We shouldn't really expect to be able to compete necessarily against those. But nonetheless, it turns out that in a sort of internal comparison, this approach does very well. So on the left here, we're just doing kernel hyperparameter optimization. So there's none of this optimizing intermediate layer kernels. Map is then maximum a posteriori inference over those underlying features, either in the deep neural network or the deep Gaussian process. And then on the right-hand side here is the deep kernel machine objective with, well, which corresponds then to this exact Bayesian inference, albeit in this strange setting. And you can see that we're doing quite a bit better. And these root mean squared errors actually, in many cases, compare quite well to what goes on in deep Gaussian processes, but it isn't clear the same is necessarily going to be true of something like a log likelihood. Okay, but ultimately, the reason I care about deep kernel machines is not the performance on some little toy data sets. You know, the point of this exercise is not to perform slightly better on some benchmark. The point of this exercise is to develop a whole new family of methods that have lots of exciting potential. And so to talk about this potential, I'm going to consider these 3 points here. So that's interpretability, unimodality, and the possibility for fast optimizers or solvers. Okay. So to start with interpretability, so at least to my mind, you can come back and interject here, please feel free in fact, I think neural network units or weights are inherently non-interpretable. So I'm well aware that you can come up with pretty pictures that look like this, which tell us little stories about what is going on, what a particular unit might be describing. But ultimately, you know, these are little pictures. I don't feel that they're giving us a mathematical understanding of what is going on, what is being represented, and certainly not one that we can sort of use as a basis for kind of building a bigger theory and bigger methods. In contrast, at least to my mind, I think kernels are inherently interpretable. And that's because ultimately, they measure the similarity of the inputs as judged sort of by the network at that layer. And so it really does, yeah, and as such, in fact, kernels tend to be used when we're talking about the theory of neural networks. So yeah, I certainly think that kernels are the way forward for pushing interpretability, and if we're working with kernels, we may as well work with deep kernel processes, because they, in addition, give you this beautiful loss function, which is very easily interpretable in terms of these kernels. So this is just like a sort of statement of my excitement about the exciting ways we can go forward. Please let me know if I drop at any point. It's just told me that my internet connection is unstable. Okay, next, unimodality. So, as I'm sure we all know, neural networks are hugely multimodal. They have super nasty loss landscapes that look something like this, and that causes loads of problems. So if you're a statistician, it means that the sort of best set of parameters, best set of weights is non-identifiable. That breaks an awful lot of proofs we might want to do. It also makes it very difficult to optimize efficiently. So most of the clever methods you can come up with are going to assume some structure, perhaps unimodality, perhaps convexity. And if you don't have that structure, if you have a big mess, it's really hard to develop anything clever. And so you just end up doing gradient descent. And if you're in the Bayesian setting, it's then very difficult to approximate either form a variational approximate posterior over such a distribution, or to even sample this distribution. Again, it's a complete nightmare. So, I mean, that raises the question, well, where does this multimodality arise? And certainly, I would argue it arises in part due to permutation symmetries in the weights. So let's consider this sort of little component of a neural network in here. So we have input units at the bottom, output units at the top, and intermediate layer units in the middle. So now, if I swap the identity of those two units, then I'm going to get exactly the same input-output function, but I'm going to get very different settings of the weights. So let's go back. And that's now a big problem, because it means that there's either sort of two modes or two optima, two global optima in my loss function, or there's two modes in my approximate posterior. And so now I've got big problems either optimizing that loss function or approximating that posterior. In contrast, as soon as I work with these kernel or ground matrices, all of these problems essentially vanish. And that's because any permutation of the weights is going to always give me exactly the same ground or kernel matrices. And that sort of automatically makes me believe that in the kernel space, these loss functions and those approximate posteriors are likely to be much simpler. But it turns out we can go even further, and we can show that for a linear deep kernel machine, and a linear deep kernel machine just implies that this nonlinear transformation of the kernel isn't going to do anything. It's just going to return the original ground matrix. And this corresponds to a linear neural network where I have my nonlinearity there just being the identity function. So if I do that, then the only solution is this thing in here. Except there's a -1 on the G0. Anyway, so this, if we look carefully at it, is going to, where here G0, that's this input ground matrix that we've seen several times before. GL plus 1 here is the same kind of object, but I'm doing it on the outputs, on those targets. If you look at this, what it says is that as for L equals 0, then this term disappears because we have a 0 power, and so GL is G0. And then as we go further and further through the network, this GL is going to become closer and closer and closer to that G of L plus 1, that output kernel. So sort of intuitively what's going on is that these ground matrices, or these optimal ground matrices, are interpolating between G0 at one end and G of L plus 1, which is this target matrix, at the other. And that gives us a really strong intuition for what's also going on in the nonlinear setting. So in the nonlinear setting, we very much expect something similar to be going on, except that you've also got these nonlinearities. And so you get to sort of exploit those nonlinearities in order to make that transition, that interpolation, easier. Okay. It should be said, in the nonlinear setting, we don't have proofs. As of yet, we have some ideas, but it turned out it's quite hard to do. So instead, we did a bunch of experiments, in particular with the 4 smaller UCI data sets, different numbers of layers, different kernels, and basically in all settings, we found that we could initialize with many, many different, quite widely dispersed settings of these matrices, and we always converge to exactly the same solution. So interestingly, this was true for the deep kernel machine objective, but it wasn't actually true for the map objective. So we did find a counterexample for the case of a map objective, which tells us both that these experiments are relatively powerful. It's not that we're starting very, very close to that optimum and just letting them all converge inwards. And it's also telling us that there might be something special about this deep kernel machine objective as opposed to other things that you could come up with. Okay. So what does unimodality mean apart from just being a nice theoretical property? Well, the reason that I'm super excited about this is that unimodal objectives mean that we've got a lot of structure on that loss landscape, and it gives us the potential to develop clever, for instance, second-order style optimizers. And at the same time, if I was in the properly Bayesian setting, then instead of having to approximate this horrendous distribution over weights, which is a nightmare and it's never going to happen, instead, I've now got to approximate what is ultimately a unimodal true posterior. And, you know, even if it's a distribution over matrices, which is kind of messy, it's still unimodal. Like, I still have a good shot at doing a good approximation of that distribution. So this is also an exciting direction, again, that's in the fully Bayesian way that I'm not going to talk about here, but you can ask me about at the end. Okay. So then we do actually have some ideas about how to use that unimodality in order to develop fast solvers. So again, I'm going to talk about a linear kernel, which is, if you remember this thing, so corresponding to the deep linear network. It turns out we can actually solve our loss function for where the gradient of a particular Gram matrix equals 0. And that's going to give us this function here. So we're fixing the Gram matrix at the next layer and the Gram matrix at the previous layer, and then we're optimizing for this GL. And if we find the maximum of this objective, then we need to solve this equation here. And it looks kind of nasty, but at the same time, it looks like something we could do if we thought sufficiently hard. And it turns out that control theorists have thought very, very hard about this for an extremely long time. And this is the continuous algebraic Ricatti equation. Turns out it's very important to them. I don't really know any control theory, so I can't really tell you why that is. But ultimately, they care about this equation. They give us a stack of solution methods that are very efficient. So there are methods based on iterative approaches, and there are even closed form solutions based on eigendecompositions of slightly extended matrices. But fundamentally, this is all like fine and roughly analogous to like a matrix inverse in terms of the amount of computation you have to do. And this approach, it was derived for the linear setting, but it can actually be adapted relatively straightforwardly to the nonlinear setting. If we do that, it will converge, or it does converge very quickly. And that means, very excitingly, that deep kernel machines have the potential to beat neural networks. And that's because we can exploit that simplicity of the loss landscape to develop very, very quick solvers or optimizers. And that's something we simply can't do for neural networks. So I'm really excited about this direction, but it is very early days. So we don't even have this work in submission anywhere. This is our next paper that we're writing on. Fantastic. So I'm going to zoom out again to some of our questions and thoughts about future work, and then open it up to you to ask me questions. So on the practical side, and to my mind this is almost the most important, or it probably is the most important, one of the key things that we're developing at the moment is scalable solvers. So taking this fast continuous algebraic Ricatti equation approach, so we have that working in the full rank case, but we don't have it working for inducing points or for like random Fourier features to try to speed that up and to get rid of that nasty cubic scaling. And then if we think about sort of the successes of neural networks, we have things like convolutions, transformers, recurrent neural networks, all of that architectural jazz that we would need to build into deep kernel machines to really make them competitive in sort of the long run. And it's kind of annoying because, you know, we have to do more math to build these things, but ultimately we believe there's a big payoff there. So we're really excited about this direction. At the same time, there's also some really exciting theoretical questions that we're working on. So this first one is the full objective in the nonlinear case unimodal. I still don't quite know the answer. I'm pretty darn sure the answer is yes, but we haven't got a proof yet. So seeing how we can use this approach to build a theory of representation learning, both in neural networks and something that I'm really excited about, actually in neuroscience as well. So it turns out that these kernel-gram matrices are actually very commonly used in experimental neuroscience. And that's because you can actually build one by using any sort of experimental technique. All you need to do is record the activity of the brain. You could do it with an electrode, you could do it with fMRI, and then look at the similarity of those representations of the activities either on the electrical or on the fMRI, and then you can build one of these similarity matrices. And that then allows you to compare these very different experimental paradigms to what might be going on in a neural network. So I'm very excited about sort of building theory in terms of these matrices as opposed to just using them as like this experimental technique. And finally, again, this, to my mind, much cleaner theoretical basis, especially this very clean objective, really should let us do, much cleverer things in terms of generalization bounds. So this might involve Bayes, it might involve something else. Unfortunately, it's not really my area, so it's difficult for me to say how generalization bounds would work in the deep kernel machine setting. I'm just darn sure that it should work and it should give us something very useful. All right, and then I'm just going to leave you now with a few of the past works that we've done building up to this. So this was the first bit of work that thought about flexibility and inflexibility in deep neural networks. And then these two are thinking about the fully Bayesian setting. And it's actually only now that we're getting onto this deep kernel machine setting, which is really more of a generalization of classical kernel methods. And yeah, we'll have those papers on arXiv in a few days, hopefully. So please do send me an email if you're interested in any of that, and I can speed that up. Great, thanks.
Thanks a lot. It was a fantastic talk, very, very interesting developments. Yeah, so we have time. I mean, yeah, we're a bit short on time, but yeah, I guess, yeah, there are a lot of questions. If anybody from the audience, yeah, Anna Koroluk.
So how implementable are those algorithms? I guess not really much, but also the computational power is growing.
So do you mean in terms of like asymptotic compute, or in terms of like practical, how complicated it is to write the code?
I mean, how realistically that you can make a code and run it?
Yeah, so I mean, the objective itself is pretty simple, really. So sorry, we'll get there. Yeah, so it's this objective. So you're optimizing this for gram matrices, and you can do this by gradient descent. So all you need to do is sort of parameterize your positive definite gram matrices, let's say by some matrix times some matrix transposed, because that gives you positive definite matrices, and then you can plug that into all of these terms and just do it. The issue then is that that's not very scalable, because it has the sort of classical kernel method cubic compute cost. So then you have to think a bit harder and do inducing point variants. The inducing variants aren't actually, they're very similar to what you get in a deep Gaussian process. So it's fine, but it's a bit more complicated. And again, the solvers, they're fine, but a bit complicated in the general setting. I mean, ultimately, what we are going to do is to build a very nice library such that you don't have to think about these things, or you don't have to think about the implementation complexity, and it will just go off and do it for you.
Yeah, that is sure, but I mean, how scalable is the code when I run it for thousands of data rows?
So it's just like kernel methods. So if you run the naive full rank method, it's cubic in the number of data points, and it's very bad. But I mean, we've already got a linear, sort of an inducing point variant, which is linear in the number of training data points. which is fine. We've scaled that up to 50,000 data points with no problems. There's no reason it wouldn't go much higher. Yeah, and I mean, that's the key to making these methods practical, and that is definitely something that we are doing, and in some cases we have done already.
Okay, thank you. So you linear. You said that it's linear with numbers of data points.
If you use these tricks with it, so to make it linear, you need an inducing point variance, or you need a random Fourier feature variant.
Thank you.
Thanks. Maybe one last question from Ardo.
Hello, long time no see. Great talk. Just a quick question. We are running out of time, but yeah, just taking up on this point that you need some approximation schemes to deal with the complexity. And you have mentioned an RBF at some point, and then you mentioned now random Fourier features and so on. So would you expect that having a stationary model in the intermediate layers is a good thing? While, for example, in Cho and Sol, they very much work with inherently nonlinear, non-stationary things. So, what is the role of can you approximate things with random Fourier features here and have models that work well?
Sorry, I didn't. Was the question just about what have we done with random Fourier features so far?
Yes, because if you use random Fourier features, you kind of have an assumption that things are probably stationary.
Okay.
Then, if you use RBF, you also had a similar assumption. But then, of course, many typical flexible models are inherently non-stationary. So what is sort of the role of can you use a stationarity assumption there? Is that okay?
No,
I don't know.
That's an important consideration. My expectation is that random Fourier features will only be applicable with squared exponential style, with isotropic base kernels. I think it should be okay even when you sort of have these kernels that are sort of adapting through. Yes. Yeah, I think it just depends on the base kernel. So I think you should be fine with random Fourier features with a squared exponential kernel as your k function. I should say that we haven't actually got a random Fourier feature method up and running yet. We've really just worked with inducing points which are a bit simpler. Certainly, there's reason to believe that for the solver, random Fourier features might work better in the long run, but there's various technical issues that we have to get around, like what happens when you're adapting this thing, but at the same time you've got these sort of randomness involved in the choice of that random Fourier basis. Yeah, so this is definitely something that we are exploring.
Interesting. I will follow your your exploration. Thanks.
Maybe I have one last question and then I'll leave to let you go. And thanks again, fantastic talk. So, yeah, so I think it's one of the starting points. I mean, well, we have many starting points and many goals that you listed. Let's say one of the things that we want to have is, we don't want not to throw away the baby with the bathwater, as they said famously. And the point is, so let's say, so in the example that you showed us, essentially, you said, yeah, we start with something close, to the squared exponential kernel, but the whole point is that we want to learn the kernel. So how far can we go to learn something which is different? So I guess to say what you have to do there, you start with some prior over kernels of expressed in some way, but let's say you also want to be able to explore and to move away. Of course, let's say, as Arno pointed out, yes, maybe there are some constraints due to stationarity, etc. But let's say, so how far can we learn different kernels? So have you explored that in the sense, of learning something which is not just some variant of some, say, squared exponential like thing?
Sorry, that seemed to be a nice description of the talk. I didn't get the question. Was there a question?
Yes, there is a question, which is, well, let's say, So in the example that you posited, let's say, so you said you started with square exponential. So let's say, so how far can you go to learn something which is different? So let's say, and this again, the other point is how to start with different priors over kernels. So let's say, what you use as a, so what's a good prior over kernels? And, say, I think these are, I don't know, maybe you said that, but I didn't see in the talk.
No, that's a good question, definitely. So there's a flippant answer here, which is that deep neural networks implicitly define a prior over kernels. So we use the same prior over kernels, switch off brain, and we can learn the same things that deep neural networks can learn. But at the same time, I realize that is not a very satisfying answer. So, I mean, this gets a bit more into the fully Bayesian interpretation of what's going on. So in the sort of fully Bayesian world, where we don't actually take this infinite limit at all, so we still have a finite number of units at each layer, then this gram matrix actually becomes Wishart distributed, which is sort of and that Wishart distribution has a sort of expectation which is given by K0. And so then your kernels, in effect, have this sort of Wishart flexibility to them. Now, Wisharts have a very specific way that they sort of alter distributions in terms of eigenvectors. And it turns out you can also choose other distributions, like inverse Wishart distributions, which have very different patterns of what they do with the eigenvectors. Sorry, with the eigenvalues. Basically, Wisharts can take big eigenvectors or take big eigenvalues and make them very small, because it's almost like you don't have any weights which care about that direction in the input space. Inverse Wisharts are the opposite, so if you give them an eigenvector which is medium-sized, it can't set that to 0, but it could set it very, very large. And that does give you sort of different patterns of priors over these matrices, but it must be said, I don't really know how to like say anything more about it than yeah, you have these options and they're slightly different.
Great, cool. Well, thanks. Yeah, thanks again for giving us this presentation. Yes, and yes, as well on my side, and we'll keep following your explorations and see where this goes. It's very exciting. Thanks.
Fantastic. Thank you.
Thanks again, and thanks also everybody for joining us and for this unusual time. And see you next time. And thanks, Laurence, again.
Thanks.